This is the problem on the monatomic gas, and it says a monatomic ideal gas expands isobarically. Using the first law of thermodynamics, proved that the heat Q is positive, so that it is impossible for heat to flow out of the gas. No numbers are given. We're not going to calculate anything. We're actually doing a proof. This is the kind of best image that I could find, where we can see an expansion here. It doesn't, what I circled here doesn't say it's isobaric expansion, but it is an expansion. And so we're supposed to figure out that as the heat goes in, and it kind of looks like it here with the red arrow, meaning heat flows in as well. So anyway, that's what it shows, but we're in the drawing, but that's what we're supposed to prove. So I'm going to write down the ideal, not the ideal gas law, the first law of thermodynamics. I actually don't need that box. And that one would be delta U equals Q minus W. So the change in internal energy equals the heat flow minus the work that is being done. And of course, work is being done during an expansion here. For example, on the piston moves out, does work here on this one. The PV diagram kind of looks like this, with PV, and then here's the expansion, and this is isobaric because the pressure stays constant, and then the heat is calculated simply as the integral, respectively the area underneath that straight line, which means it's this rectangle here. But this one here is where we're looking at the isobaric expansion. The work, of course, is going to be positive, but I'll show that in a moment. Here's where we're supposed to figure out the Q. Is it positive or negative? Is the heat flow going in or out? So just one algebra step, Q equals delta U plus W. That this one is a plus here, and there's a plus in front of it. Doesn't mean anything because the delta U could be positive or negative, and the work could be positive or negative. This is just the algebra here. Okay, the work, as we see in the chapter, is given as P times delta V, so pressure times the change in volume, and the internal energy is given as, or the change in internal energy is given as from the previous chapter, 3/2 N R delta T, and then there's that plus in between. Okay. At this point here, we can already decide that this part here is positive because it's an expansion. The delta V here, so from going here to there, must be positive. The pressure is always above zero. There are no negative pressures, so therefore this part here, this term, is positive anyway, and now we have to figure this one out. Well, for this one, I'm going to use the ideal gas law. So I'm going to do 3/2 NR, and then instead of delta T, I'm going to write P times delta V, and I'm allowed to do that because the pressure is the same and the volume is the only one that changes, divided by NR, and then plus that P times delta V. And now we can see all these numbers are positive here, of course, N and R divide, and here we have P delta V, here we have P delta V, and so that means that this term is positive, this term is positive, and therefore overall the heat flow is positive. And when we write a proof, we can write QED, quod erat demonstrandum, what has been shown. Also, with the delta V being positive and being positive here, that means that the temperature actually increases, which at this point we didn't know. As the gas is expanding, for example, in an adiabatic expansion, which goes very fast, where we don't have any heat flow, so the Q equals 0, the temperature actually goes down. Apparently, in an isobaric expansion, the temperature actually goes up, and that's what we showed from here to there. This is also a problem about a monatomic gas, and it says the work done by 1 mole of a monatomic ideal gas, gamma equals 5/3, and expanding adiabatically is 825 joules. The initial temperature and volume of the gas are 393 kelvins and 0.100 cubic meters. Obtain A, the final temperature, and B, the final volume of the gas. First of all, the only reason that they tell us it's a monatomic gas is because they derived in the book the adiabatic index gamma equals 5/3 only for monatomic gases, and for diatomic gases such as O2 or H2 or N2, so nitrogen, oxygen, hydrogen, they didn't develop them, but they would have to give us a different one of 7/5, which then is 1.4. And here for monatomic ones such as helium, krypton, xenon, so all the noble gases, they would give us 5/3, 1.67. And if we had like triatomic gases like CO2 and H2O vapor, we would have to be given 8/6. Depends on the problem, but for the most part, that's the reason why they give us the monatomic gas, because they have already derived that gamma for us. So here again, I chose the same drawing that was supplied in the software, and that would be an expansion here, and in this case it would be an adiabatic expansion, and then actually there is no heat exchange, so when they put red on here, that shouldn't happen. So it's kind of, it's not representative of what we have here, but that's the closest I could come up with some kind of expansion. It's an adiabatic expansion, and let's see what I'm going to do here. So I need more space. Okay, so the PV diagram looks kind of like this. PV, and then we start somewhere here, and it's an expansion, so it goes to the right, and then the pressure is supposed to go down. So we're going to have this one here, this kind of curve, and then it ends up here, and then the area underneath, that's the work done, and they give that to us. So let's see, the work done is 825 joules, so they give that to us. The heat is applied because it's adiabatic. There is no heat flow, so that comes out to 0. And because this one is 0, then delta U indeed equals negative the work. So when 825 joules are done by the gas, then that means that the internal energy has to go down by 825 joules. So this one is done as well. Then let's see, they tell us what the initial temperature is. So I think I'm going to write Ti. Yep, I'm going to write Ti, that is given. They tell us what the initial volume is. So that one is given. And then they ask us what is the final temperature and what is the final volume of the gas. So final temperature and final volume. First of all, I'm going to look again at the PV diagram. So here we start out with some kind of pressure, then we end and volume, then we end up here with a smaller pressure and larger volume. And what happened to the temperature is during an adiabatic expansion, with the internal energy going down, I said earlier that's the negative of the 825 joules of work that were done. Therefore, the temperature has to go down. So during an adiabatic expansion, the temperature decreases. So our final temperature needs to be smaller than our initial temperature, and obviously our final volume has to be larger than the initial volume. They ask us first to figure out what the final temperature is, because when you peruse the equations that are given in this chapter, first of all, we can only use the ones that have the word adiabatic in front of it, or the ideal gas law. that applies to everything, but for example, we cannot use an equation that specifically says this is only for an isobaric process or this is only for an isothermal process. We have to use the ones that either say adiabatic process or it's not specified, as I said, such as the ideal gas law that always applies. So one of the equations here actually says that the work equals 3/2 times the number of moles times the ideal gas constant, and then parentheses the initial temperature minus the final temperature. And I wrote down the correct equation, and you may have already seen what I overlooked earlier. The number of moles indeed is given. They tell us it's 1 mole, and when I wrote down the variables in my table here, I spaced that it's actually given as 1 mole, and notice that everything in here is given, and that means that this is actually for part A, that the final temperature equals work divided by 3/2 nR minus Ti when I get that to the other side. So I divide by all of this here, the work, and then I subtract the initial temperature, but then I still have a negative in front of the Tf, get that negative to the other side, so that one here changes then to a positive, and then one changes to a negative. So all we have to do is plug in the numbers. So we have negative 825 joules divided by 3/2, 1 mole, and 8.314 is the ideal gas constant. Top of my head, actually. I kind of have that memorized. 8.31 for the ideal gas constant, and then add to that the original 393 kelvins, and you come up with some number, of course positive because we're in kelvins, so some positive number in kelvins, around 320 kelvins. Okay, for part B I need a lot more space. So part B, what we're going to do there, we have to figure out what the final volume is. When you look at the equations for an adiabatic process, we need the pressure because they give us this equation, Pi Vi to the gamma, and of course the gamma is 5/3. They tell us that. I could also write this down here. So gamma is given. And that equals Pf Vf gamma. And neither we haven't given neither one of the initial or final pressures. So the question is, can we actually use this equation? Well, because we have two unknowns here, we need something else. We could, for example, write down the ideal gas law. The ideal gas law always applies, and it kind of looks like that this one here is a new ideal gas law, and it's not. It's actually the same as this one over here. And of course, yeah, you can argue definitely there is an exponent here that doesn't exist over here. But what that exponent does here is it gets rid of the temperature, which during an adiabatic process changes, and in getting rid of it, it introduces that adiabatic index. So this one here is kind of an abbreviation for the ideal gas law having kicked out the temperature. It only says pressure volume, and keep in mind the temperature does change, and the exponent gamma is substituted instead for that. Now, what we can do is we can take this formula and plug it in here, and then derive something that has something in temperature and volume with, again, the gamma in there as an exponent, and then we can do the same thing for pressure and temperature. So all these three variables, P, V, and T, can be thrown around, and the adiabatic law can be made look can look a little bit different. By the way, in the book, all they say about the derivation of that equation is that it's done by integral calculus, and I got this here from Wikipedia, and if you were to follow this one here on the adiabatic process on Wikipedia, indeed that's what they do. They introduce another parameter called alpha, and then at the very end they substitute the gamma in for this alpha here, and there it is, PV to the gamma. And then, as I said, for the others they would do something really similar, like, let's see, boy, where'd it go? I think this is the one. Yeah, here's the one for temperature and pressure, and then somewhere in between is the one for temperature and volume. At this point, my solution manual says, take the ideal gas law, plug it in here on both sides, get rid of the pressure that we don't know, and then what we are able to introduce is the V here and the T, and we come up with an equation in volume and temperature, and therefore can solve then for the only unknown that's left, the volume here. But there's a second way of doing it, because when we look at the ideal gas law, again, this is applicable at all times anyway. Then notice that for the initial part, we have the initial volume, we have the initial temperature, we know it's 1 mole, and so all we need to do is solve for pressure. There we go. And come up with nRT initial, which we know, divided by the initial volume. And so that comes out to, let's see, 1 mole times 8.31 times 393 kelvins divided by the initial volume of 0.1 cubic meters. So it's all in standard units. And I come up with a pressure of, let's see, 3 significant figures, 32,700 pascals. Okay, and that means now I know what the left-hand side is going to be. The left-hand side, therefore, is going to come out to 32,700 pascals times, and I'm going to use here on my calculator, it says 32,658.3, so I'm just going to use that one, times the initial volume of 0.1 cubic meters, and that needs to be to the 5/3 power. That's the adiabatic index, and I come up with, on the left hand side, with 704 rounded, 703.60, 704 rounded, equals PF times VF to the gamma. And then I notice I actually do have to plug that in because I still have 2 unknowns here, and here I also have 2 unknowns with the final temperature given, so I'm going to plug this one in here anyway. So I'm going to have 704 equals, and getting rid of the pressure that I don't need, I'm going to say nRTF divided by VF times VF to the gamma. And actually, in hindsight, it does look quite convoluted at the end. 704. There was nothing better to do. This is, of course, a 4 as usual. nRTF, which we know, times VF to the gamma minus 1, one of the laws of the exponents. And then to solve for VF, it would be 704 divided by nRTF parentheses, and then in order to get rid of the gamma minus 1, I need to take the root on the other side, and that can be written as such: 1 over gamma minus 1, again with some law of the exponents, and I come up here with something, and because everything is in standard units, this will also come out to cubic meters. And then I might as well do it. So I'm going to do this one up here. I'm not going to write it down, by the way. So I'm going to do this one up here, which says negative 825 joules divided by parentheses 3 over 2 times 1 mole times 8.31 parentheses, and then add to that the original 393 kelvins. And I come up with a rounded 327 kelvins right here. And then I take the 327 kelvins and plug it in right here. So this is going to be 704. Remember, this is always smeared. Whenever the software gets a chance, it smears out the 4. That's a 4. This is a 4. There we go. So parentheses 704 divided by 1 mole, or again another parentheses, 1 mole times 8.31 times the 327 kelvins that I just calculated, close the parentheses again, and then to the 1 over 5/3 minus 1, and I have to close again several parentheses, and I come up with a rounded 0.132 cubic meters, and that's what I said earlier, that so 0.132 cubic meters, that the volume of course has to become larger as it expands. There's a problem about geothermal energy, and it says a power plant taps steam superheated by geothermal energy to 505 kelvins, the temperature of the hot reservoir, and uses the steam to do work in turning the turbine of an electric generator. The steam is then converted back into water in a condenser at 323 kelvins, the temperature of the cold reservoir, after which the water is pumped back down into the earth where it is heated again. The output power, work per unit time of the plant, is 84,000 kilowatts. Determine A, the maximum efficiency at which this plant can operate, and B, the minimum amount of rejected heat that must be removed from the condenser every 24 hours. This here is a schematic of how such a geothermal energy production plant can look like. Obviously I got this from a website from Iceland, which is the front runner in the world for geothermal energy, simply because that's a volcanic island, and as you can see here, the heat comes up, and that then drives the turbines, and then it's being pumped down now as cold water again, and then it comes through here and again superheated and comes back through here. So it's kind of cycle here. So here we have the hot reservoir and the high temperature, and here we have the cold reservoir and the cold temperature. The schematic from the book is this one here. So here we have the hot reservoir, heat goes into the engine, the turbines, work comes out in this case as electrical energy, and then the excess heat goes back into the cold reservoir, and yeah, as this one here shows, then it starts over again. Okay, let's see what we have given in the problem. And that is, we have the two temperatures given, so the high temperature as well as the cold temperature. So TH is given and TC is given. And in the previous problem, I wrote these as TI and TF according to what they give us, the kinds of equations that they give us in the book, because I realize it as such initial temperature, final temperature. Here I realize it as that we're talking about cold temperature, hot temperature, and so I might as well label them like that. We're supposed to figure out what the efficiency is, E. Then what else we have given is the output power of the plant is 84,000 kilowatts. So we have given, capital P for power. And we're supposed to figure out what the rejected heat is that must be removed, and that would be the QC. So there's a question mark there. And then we have one more given, and that is must be removed from the condenser every 24 hours. So we also have time given, and we'll see where that one plays into. Okay, the very first part, A, is really straightforward. The title of the section is Carnot's principle and the Carnot energy in engine. So in this case here for this problem, we have to assume that indeed we're dealing with a Carnot engine, and basically why the book keeps doing that with the Carnot engine, because the equation for that is really simple and can be written as E equals 1 minus Tc over Th. So here all we have to do is plug in the numbers, and you come up either as a decimal or as a percentage. And so that would be 1 minus 323 divided by 505. That gives us the decimal, and then move the decimal point twice over, and we come up with the percentage. Of course, our temperatures both have to be in kelvins. They already do that in that problem, but be aware if you get a problem that gives a temperature in Celsius, you have to convert that first, because you need to have absolute temperatures in the metric system and kelvins in the American system in Rankins. By the way, there's also the equation for the efficiency of 1 minus QC divided by QH. Now that equation is the same for, whoops, I don't know why that jumped, is the same for all engines. That's always applicable, and for the Carnot engine itself, it becomes this easy, simple expression here, 1 minus Tc over Th. That's not the case for other engines. For example, for the diesel engine, this is the formula. This one right here looks pretty bad. In fact, the alpha here is what is called the cutoff ratio, so a ratio of the two volumes. You go through the PV diagram and you have 1, 2, 3, 4 points, and each one of them is a certain volume. And so here you have a certain ratio of the volumes, and then the R is the compression ratio, V1 over V2. Of course, they depend on the temperatures as well, and of course the gamma is given as the adiabatic index. And yeah, the equation looks quite bad, and for a internal combustion engine, the Otto engine, it looks just as bad. And that's why they tell us, just use it in approximation as being a Carnot engine, even though that's not true, but at least the equation is relatively simple. Okay, for part B, how can we figure out what the heat is that needs to be rejected from the condenser? Well, the one equation that we have actually we have two equations. The one that I already wrote down here, but we don't have QH. We are supposed to figure out what the heat is that is being rejected, but we don't have the amount of heat that comes in. So, if we use that, we'd have two variables. The other equation is this one here, the conservation of energy for a heat engine, QH equals work minus Q plus QC. And again, we have two unknowns, QC and QH. The W is given. That was the 84,000 joules. Yeah. Oh, I'm sorry, 84,000 kilowatts, which is 84,000 kilojoules per second. Again, here we have two variables though, QC and QH. However, there is a second equation that we can apply now, which is that the efficiency is work divided by QH. So QH is the same as work divided by efficiency. So when I substitute that in here, work divided by efficiency, which I, by the way, just calculated. Then I come up with this one, work plus QC. Okay, and then the only unknown that I have is QC, so it's going to be QC equals work divided by that efficiency minus the work. And then I take back what I said a moment ago. Work is not 84,000 kilojoules per second. Work has to be in joules, but that's where the time comes in. The work that is given or that is being calculated or can be calculated by power, that's the power that's given in the problem, 84,000 kilowatts. Power times the time that is also given as 24 hours, but that has to be converted into into seconds. And so this one is going to be 84 million watts times 24 hours times 3,600 seconds. Divide by that efficiency that was calculated up here, out of the picture at this point. So calculated up here, and then divide by that efficiency minus again the 84 million watts times 24 hours times 3,600 seconds. Overall, for the rejected heat, you come up with a pretty large number, and that will be then in joules, 10 to the somewhere around 10 to the 13 or so. This is the problem for the car engine. I couldn't find any better diagram, so I'm just using this one there. And it says, suppose the gasoline in a car engine burns at 631 degrees Celsius, while the exhaust temperature of the cold reservoir is 139 degrees Celsius, and the outdoor temperature is 27 degrees Celsius. Assume that the engine can be treated as a Carnot engine, a gross oversimplification, and I mentioned that earlier. Why we're doing that? Because the equation becomes rather simple for the efficiency. In an attempt to increase mileage performance, an inventor builds a second engine that functions between the exhaust and outdoor temperatures and uses the exhaust heat to produce additional work. Assume that the inventor's engine can also be treated as a Carnot engine. Determine the ratio of the total work produced by both engines to that produced by the first engine alone. Now, one could say, well, why isn't there such a thing? Well, probably building such a second engine would kind of double the space needed for these two engines in a car in order to increase efficiency, and then you have more weight and you have more maintenance and so on. Okay, third time might be a charm. This is actually my third take on this one. I first made a mistake. I'll show you in a moment, and then I made another mistake of slightly unplugging the microphone, so my second take, which was the corrected version, was mute. So I'm actually not writing at this point, I'm just taping over my already recorded recording. And so what we have sitting here is the high temperature is given for the first engine, the cold temperature is given for the first engine. We're supposed to figure out what the efficiency is for that first engine. And then the high temperature for the second engine is given, and by the way, that should actually read E2 there, the question mark. I guess I forgot that entirely. And then the high temperature for that second engine is the temperature of the rejected heat from the first engine. That's why it's also called TC, and then its low temperature is TA. And so here I continue with my kind of muted recording, and then all of a sudden it jumps to something there because I've already written it down. There we go. And what I'm saying here is, here's what I first wrote down here is what they actually want to know is the ratio of the total work of the two engines together, so work 1 plus work 2, the ratio of that to the work of the first engine just by itself, and that's why I wrote question mark. Then I wrote down the efficiency for the first engine, as 1 minus TH over TC, but that's the actual mistake I made. And then I just kept going and noticed that later on, oh wow, at the very beginning I made this mistake, and so here I believe I'm about to erase that. And of course it's supposed to say that the efficiency of the first engine is 1 minus TC over TH, the cold temperature over the high temperature. And when you plug in the numbers, you have to say that the cold temperature is not 139 degrees Celsius, but you have to convert that to kelvins, so 412 kelvins. And then the high temperature is not 631 degrees Celsius, but 904 kelvins. And you plug those numbers in, and you can write them as a decimal or a percentage. But either way you do it, it's probably better to write it down as a decimal because you will need it later. That's why I pointed at the work equation up there. For E2, the efficiency E2 would be the 1 minus the colder temperature, which is the air temperature, minus the TC, which is the high temperature for the second engine and used to be the cold temperature from the first engine. And again, that's the rejected heat that goes into second engine. Again, that comes out to a decimal or a percentage. So the air temperature is not 27 degrees Celsius, but 300 kelvins is what you have to plug in. And of course, for the TC, again, you have to plug in 412 kelvins. So you come up with decimals for both of these efficiencies. Okay, let's see what's going to happen next. I'm not exactly sure why I pointed these here. So probably because I'm kind of describing here it over the muted microphone, and of course I can't repeat myself verbatim throughout the entire problem. I'm going to give myself a little bit of time here, and I think the next thing I'm going to do is I'm going to pull down that equation W1 plus W2 over W1. So there we go. And now I'm going to see what else I have. And the book also says that I can calculate the efficiency if I know what the work is and the input heat, and write it as work equals efficiency times the input heat. However, I don't know that input heat, but we'll see that it'll work, that once I actually plug these in here, that we will come up with a result. Okay, now for W2, I'm going to do something similar, and the work 2 of for the second engine is the efficiency of the second engine. And again, in the very top right corner, it should say E2, not just E. So efficiency of the second engine times the heat input to the second engine, which is the rejected heat from the first engine. So that's why I can write QC. Now I substitute all of that into that W1 plus W2 over W1 and come up with this expression. Again, from my very first take, I had that already prepared, so I'm plugging it in. There it is. And I'm looking at two terms divided by the denominator. And what these two terms here doing is, so as I divide the first term by the denominator, of course that's the same, so I come up with 1, and that kind of justifies that I can actually use these unknown QH and QC because they seem to divide out. Now I look at the second term, QC over QH, and I notice that I also got an equation for that, which is that the efficiency equals 1 minus QC over QH, which is the same for all engines. And I'll correct it in a moment. I will put a C there on the numerator for the QC. There it is. Okay, so now I'm going to plug that in there. First of all, I'm going to have, I guess I'm going to say again that these two are 1, and then on the second one it's E2 over E1. And now I'm going to plug in QC over QH for the first engine, which when you look at it is 1 minus the efficiency. And because this is about the first engine here with the QC QH1, that must be 1 minus the efficiency of the first engine. And then that equals, so, and then here I'm explaining, well, this is why I was able to use these heat flows even though I don't know them, because at the end they divide out anyway because of that extra equation that I had, the 1 minus QC over QH. I was able to manipulate in such a way that they actually divide out, and all I have in my final equation is known variables that I calculated earlier. And then that of course equals some kind of ratio. It's going to be in the neighborhood of like 20% higher, so the second engine produces 20% more work than the first engine. This is the problem on the boiling water reactor, and it says a nuclear fueled electric power plant utilizes a so-called boiling water reactor. In this type of reactor, nuclear energy causes water under pressure to boil at 285 degrees Celsius, the temperature of the hot reservoir. And again, that's a much higher temperature than under normal standard temperature and pressure, because it is under higher pressure. After the steam does the work of turning the turbine of an electric generator, the steam is converted back into water in a condenser at 40 degrees Celsius, the temperature of the cold reservoir. To keep the condenser at 40 degrees Celsius, the rejected heat must be carried away by some means, for example by water from a river. The plant operates at 3/4 of its Carnot efficiency, and the electrical output power of the plant is 1.2 billion watts. A river with a flow rate of 100,000 kilograms per second is available to remove the rejected heat from the plant. Find the number of Celsius degrees by which the temperature of the river rises. And I would say that by which the temperature of the 100,000 kilograms that are being put through of the river rises, then, because after that, so downriver it has become hotter by a certain amount of Celsius degrees, but then of course it cools itself off, and then before it gets through there, of course it's at its normal temperature. So it's not the entire river that is being heated up by that, but whatever is being pumped through, and that is the 100,000 kilograms per second. Okay, looks quite involved. Overall, what they want us to figure out is a increase in the temperature of the river water. Let's see what we have given. We have given the temperature, the high temperature of the reactor. I'm sorry, not the reactor. The water. And we assume that the problem says that the steam is going to be at 285 degrees Celsius. I think it implies that very well. And then the steam is going to go back to a cold temperature, respectively condenses to a cold temperature of 40 degrees Celsius. Of course, both of these here have to be in Kelvin, so they're going to be 558 kelvins, top of my head, and 313 kelvins is what we need. It says that the plant operates at 3/4 of its Carnot efficiency. So at some point, I'm sure we have to determine its Carnot efficiency and then take 3/4 of that. The electrical output power of the plant is 1.2 billion watts, so that one is given. And then what else is given is that the river has a water flow rate of 100,000 kilograms per second, so mass over time is given for the river. Okay, let's see, how are we going to come up with this delta T here? Well, the river is going to absorb a certain amount of heat. So the heat that goes into the river warms the river, at least those 100,000 kilograms every second. So there's that delta T. And then, of course, here, that would be simply the specific heat capacity equation, where we have, of course, the 4,186 is given. And I have to look that up, what kind of units those are. I never remember them, so I just look it up. 4,186 joules per kilograms and Celsius degrees. And then the mass here, well, what is given is not the mass, but the mass over time. So what I can do here is I can divide the left-hand side by time, and I can divide the right-hand side by time. So that means now I have I have here a known as well, and I have a known here, and I have this one here is my unknown, my variable, and this one here is kind of known as well because it's the heat that goes into the river per time unit per second, and that one is determined from the efficiency, which we determine in a moment, and the total output, the power. Okay, so let's do the efficiency next. The efficiency is, of course, for Carnot engine, 1 minus Tc over Th. Okay. Then I have to determine what the Q is that goes into the river, and for that one I actually need two equations. I need the energy conservation, QH equals the amount of work plus QC. And this one here I kind of know from the power. This one here I'm supposed to determine, and this one here I don't have given, but I can kick this out here by using this equation. E equals 1 minus QC over QH. So like that. And when I plug into one of these equations into the other, for example, I can write E equals 1 minus QC over work minus QH. Work plus QC, that's what I meant to say. Because once I plug this in here for the QH, I come up with this here, work plus QC, and now of course I have this variable here, and that work here that is being done is of course the power output of the plant, respectively the difference between it's per second, so that's a connection between the two. And then I do the algebra on this one here, and you can do the algebra yourself. I'm going to just do this here on the side for the next half minute, and in doing so, this is half a minute later, I multiply everything here with W plus QC, and then I do a little bit of algebra on this one here, and I come up with an expression that I believe is not too difficult. 1 minus E divided by E times work. Now again, that is actually not given. The work isn't actually given. What is given is the power output, but of course the power output is joules per second, and they tell us that 1.2 billion watts or joules per second. So I'm going to use that. I'm going to write here that on the left hand side, on the right hand side, that is 1 minus E over E times the work per time unit. And then of course on the left hand side, that's QC over the time, as I divide both sides by the time. Of course this one here is power, so I can also write it as such, 1 minus E over E times power. And now I recognize that this one here of course is the same as this one here, because that's the heat that goes into the river. So what I do overall is I calculate what the efficiency is. There we go, come up with some kind of decimal. I take that efficiency, plug it in here with the 1.2 billion watts. I come up with how much energy goes into the river each second. Use that in here, and then divide by C, 4,186, divide by the 100,000 kilograms per second, and I come up with a delta T. So for all of these ones here that I kind of circled, that's the calculations you would have to do. And so from that, overall, from these three equations that I just circled, you have to come up with the delta T. You will see that that is a positive number, which would make sense because the river is heating up, and that's going to be in Celsius degrees. It's going to be a few Celsius degrees. Okay, and then of course I forgot one little thing, which is that this one here needs to be multiplied by 3/4, because that's what the problem says. It operates at a efficiency of 3/4 of the Carnot efficiency. So both of these numbers here, but the rest of the calculation is the same. This is the problem on the Carnot refrigerator, and it says the inside of a Carnot refrigerator is maintained at a temperature of 277 kelvins, while the temperature in the kitchen is 299 kelvins. Using 2,500 joules of work, how much heat can this refrigerator remove from its inside compartment? Okay, so what is given in this problem is the high temperature, is the cold temperature, is the work that is being inputted, and what we're supposed to figure out is that the heat that is being removed. So QH. Hold on, I take that back. It says that is QH is the heat that is being dumped into the kitchen, and they want to know how much heat can this refrigerator remove from its inside compartment. So actually what they do want to know is QC. That's the heat that is being removed from the inside of the refrigerator, and then you would add the electrical work to it, and that would be the total QH that is being dumped into the kitchen. And there should of course be a question mark right there, because that's what we have to figure out. Okay, there are a number of equations that deal with this. For example, one of them that we find in the book is that the coefficient of performance, or abbreviated COP, equals QC over W. So the amount of heat taken out of the refrigerator divided by the work, the electrical work that goes into removing that heat out of the refrigerator, and that gives us the coefficient of performance. Now this one isn't given, this is an unknown, this one is given, so we need something else besides that. And another equation that we could use would be simply this one, that the heat that goes out is the same as the work that is being inputted plus the heat that is taken out of the refrigerator, which of course goes with this diagram from the book, where the work is going in and then it takes, that's what's being used in order to pump out the heat and put it into the actual warmer environment of the kitchen. And here you have it, QH equals QC or plus W. And of course this diagram here is of some kind of refrigerator, something I found on the internet, the way a refrigerator looks like in cross-section, the principle of it. This one here is really a schematic of it, and this one here is a little bit more detailed attached to it. Okay, still, this one here has two unknowns. We don't know how much heat is being dumped into the kitchen, and this is what we're supposed to figure out, and the two don't overlap because they have two different variables, so we're still looking for something else. And this is the equation that we could use, this following one here, QC over QH equals TC over TH. And obviously we had to do something here with the temperatures because that's given, so we're supposed to figure something with the temperatures out. Now this one here says a Carnot engine, but on the Carnot engine it says it's a reversible engine, and therefore that equation holds for the engine as such, as well as when it's in reverse, where it has become a heat pump or a refrigerator or an air conditioner. So this one holds here, and then when we determine this ratio, well, we can figure out what this one is. Of course, on this one over here, I could divide by QC, and then I'm going to come up, so this is this equation here. The second one is going to be QH divided by QC equals work divided by QC minus 1, I'm sorry, plus 1 because I divided that one by QC, and then I plug in the temperatures, so I'm going to come up with TH over TC. Of course, the temperature is in kelvins, as I mentioned. TC equals W over QC plus 1, and then I solve that equation for the heat that is being removed from the inside of the refrigerator, and that is, if you want to look at the algebra yourself, is going to be get the 1 to the other side, multiply by QC, and then divide by the TH over TC minus 1, so W over TH minus TC minus 1, and then you come up with something here, and because this is in joules, this doesn't have any units, you're going to come out with something here in joules. Relatively large number. Also, we kind of like in more than 10,000 joules is being removed for every, how much was that? 2,500? Yeah, 2,500 joules that is being put in. And overall, we actually didn't need this equation here. The COP isn't given, and it turns out that we're not determining it during the overall problem. However, if I was to determine this, and let's assume that I already know what the QC is that is being calculated here and divide by the 2,500 joules, I come out with a coefficient of performance of about 15. Now, what does it actually mean? Well, what it means is that you put a certain amount of work into the refrigerator and you remove 15 times as much energy from inside the refrigerator. And that's so what the COP means is the ratio between the energy that's being removed and the electrical energy being put in. It's important not to write this COP as an efficiency or as a percentage, because notice that this 15, if you move the decimal point here, becomes an outrageously large percentage, and that just doesn't sound right. And the refrigerator definitely does not violate any kind of energy principle. In fact, it says so right here, that right there, that energy is being conserved, but what the work is doing, for a minimal amount of work, a lot more energy is being removed and dumped somewhere else. It's not being generated, it's just being moved to somewhere else. And that's what the COP means. 15 times as much energy is being moved somewhere else than is actually needed in order to move it. This is the problem on the air conditioner, and it says a Carnot air conditioner maintains the temperature in a house at 297 kelvins on a day when the temperature outside is 311 kelvins. What is the coefficient of performance of the air conditioner? Okay, what's given is the high temperature that is inside the house. 209, I'm sorry, that's outside the house, 311 kelvins, that's 38 degrees Celsius. Whoa, this is like 110 outside. And inside the house, it's 297 kelvins or 297 kelvins, 24 Celsius, or in the neighborhood of 80 Fahrenheit inside the house. So the house itself is already pretty warm. But we need the Kelvin temperatures anyway, so I didn't have to convert them a moment ago, but I just did that to illustrate. Then we're supposed to figure out what the COP is, and we basically just have one equation in the book for the COP, and that one is the amount of heat that is being removed from the inside of the house. So let's see, in this diagram here, there's the exhaust heat going this way. Here's the heat going in, this one here. That's the heat being removed, and then the same air, of course, being pushed out, but now it's cooler. So that heat goes in here. Then there's electrical energy that moves that heat to the outside, and then the exhaust heat out here is that energy that is being removed from the house plus the work that is being inputted. So here's the work, and what I just said in mid-air was that the QH, the exhaust heat, equals the electrical work that is being put in plus the heat that is actually removed from the house. Okay, none of these we know. We don't know any of these. So what can we do with that? Well, here's one thing we can do. I'm going to write it as such that I only have QC's and QH's. So I'm going to have QC divided by QH minus QC. And now I go back to that one equation that says that a Carnot engine is reversible, and therefore it can also be treated as that. This equation you can also be treated for an air conditioner or refrigerator or heat pump. So QC over QH, I'm going to use a different color, QC over QH is the same as TC over TH. And when I plug that in, I'm going to come up with this. So the COP equals TC over TH minus TC. And what I just did, that's not quite true. I shouldn't do that. But when I really do the algebra, then this is what happens. COP equals, for example, I can divide all of this here by QC, and then I'm going to have 1 divided by QH over QC. As long as I divide both the numerator and the denominator by the same number, I haven't changed anything. Now here I can plug in that TH over TC. There we go. And I think you can see that from here, going from here to here, I divided everything by QC. That of course gives me a 1 here and a 1 there, and then of course the fraction QH over QC. And here I used this one here, plugged in the temperatures, and now when I multiply everything again with TC, I come up with this expression that I kind of pulled out of thin air a moment ago, but it is correct because I just showed you the algebra. And then this one here is going to come out to you with some number here with some coefficient of performance, and top of my head it's like somewhat over 10 as the coefficient of performance. That means you put in, let's say, 100 joules of electrical energy, and you're able to pump out 2000 joules of energy. That's what the COP means. Again, it has no units.